Let's look at an example of trigonometric substitution. Suppose we want to find the following integral. Integral of the square root of x squared plus 2x minus 3 divided by x plus 1 dx. Now in this case, we can think that we can use trigonometric substitution because of the square root. This is a very important thing to keep in mind. Whenever we have square roots, we can get rid of them by using trig substitution. If we want to use trig substitution, then we want to complete the squares. Because in this case, we have a general square. We don't have just a square and a number. So the very first thing we need to do is to complete the squares. In other words, we want to complete x squared plus 2x minus 3. Now, there are different ways to do this. And one very easy way is to compare this with a perfect square. This is the blueprint of a perfect square. In this case, we have that x squared corresponds to a squared, 2x corresponds to 2ab, and the idea is to find what will correspond to b squared. By doing this, we can complete the square. So from here we have that x equals a, then this will mean that 2x equals 2xb, which gives me that b equals 1. So in order to complete the square, what I need to do is I need to add a 1. In other words, when I complete the square, this will give me x squared plus 2x minus 3 is the same thing as x squared plus 2x plus 1. And in order to make this equality, I would have to subtract a 4. So this part right here, I can write it down as a perfect square, which is x plus 1 squared minus 4. So we can rewrite our original expression as follows. We can write this down as the square root of x squared plus 2x minus 3 divided by x plus 1 dx equals the integral of the square root of x plus 1 squared minus 4, whole thing divided by x plus 1 dx. Again, the advantage in here is that we have a square minus a number, and now we can use a trig substitution for this. In other words, we're looking for a square minus a number, which can be paired with the identity secant square minus 1 equals tangent square. So the idea is that we're pairing the square and we're pairing the number in here. So notice that whenever we do this, we're trying to set it equal to x squared minus 4. So the squares match, but the numbers don't match. So in order to have the same identity, I can just multiply the trig identity by 4, and I will get 4 secant squared theta minus 4 equals 4 tangent squared theta. So in this case, we finally match the numbers. So then that means that the squares should match to each other, which means that x plus 1 squared should be the same thing as 4 secant squared theta. And if we take the square root, that will give me that trig identity that I was looking for. X plus 1 equals 2 times secant theta. So this is the trig substitution that we're going to do. And if we take derivative on both sides, then we'll get dx equals 2 times the derivative of secant theta, which is secant tangent. So these are the two things that we need. Going back to the integral that we have, that means that we can write it down as follows. We can write it down as the integral of the square root of x plus 1 squared minus 4 divided by x plus 1 dx. And applying the trig substitution, this will give me the integral of the square root of, instead of x plus 1, I write down 2 times secant theta d theta, this squared minus 4 divided by, and again, instead of x plus 1, I use 2 times secant theta d theta. And then I just multiply by dx, which in this case would be 2 times secant theta tangent theta d theta. So let me try to simplify this expression a little bit more. Notice that the 2's cancel, secant cancel, so I would end up with the integral of the square root of 4 secant squared theta minus 4 times tangent theta d theta. Now we can distribute the square root. So this will give me the square root of 4 times the square root of secant square theta minus 1 times tangent theta d theta. So square root of 4, that is just a 2 that becomes in front of the integral. And then we can apply a trig identity for the square root. So that becomes just the square root of tangent square. That's the original trig identity that we had up here. So whenever we have this, we just simplify all the expression, and this becomes 2 times the integral of tangent theta times tangent theta d theta, which becomes 2 times the integral of tangent square theta d theta. Now, in order to work out this trig integral, we can apply again the same identity as before, and this becomes 2 times the integral of secant squared theta minus 1 d theta. So again, tangent square is the same thing as secant square minus 1. And now this is a more straightforward integral, because secant square is the derivative of tangent, and 1, well, we can take the antiderivative for that. So this becomes 2 times tangent squared theta minus 2x plus a constant. So now we have the expression we were looking for, but we have this answer in terms of theta, and we need to have this expression in terms of x. So in order to go back in terms of x, what we do is we plug the substitution into a right triangle. Remember that the substitution we did was x plus 1 equals 2 times secant theta. So if we rewrite this, this becomes secant theta equals x plus 1 divided by 2. Now secant is the same thing as 1 over cosine, which means that using SOHCAHTOA, this will become hypotenuse divided by adjacent. So I can just read off this fraction over here, because this is telling me that the hypotenuse of this triangle is x plus 1. And then it is telling me that the adjacent side for theta is just 2. So if I locate theta to be this angle over here, that means that the adjacent is going to be 2. Now what we need to do is we need to find tangent, and we need to find theta in terms of x, basically. So first of all, in order to find tangent, we just remember that tangent can be written in a similar way. This will be opposite divided by adjacent. So in this triangle, we can find the opposite just by using the Pythagorean theorem, which would be the square root of hypotenuse square minus the adjacent square, which in the end is a very familiar expression. That would be just x plus 1 squared minus 4, which is exactly the same thing that we had up here whenever we completed the square. So this means that this is the exact same expression we started with. That means that the adjacent side, in our case, is going to be just the square root of x squared plus 2x minus 3. So this gives me tangent to be opposite, which is the square root of x squared plus 2x minus 3 divided by the adjacent, which is 2. And then finally, from the original expression that we had up here, we can find what is the value of theta in terms of x, because theta would end up being the arc secant of x plus 1 divided by 2. We just do the inverse trig function with that. So if we put everything together, that means that the answer can be written as 2 times tangent squared. So that will give me the square root of x squared plus 2x minus 3 divided by 2, everything squared, minus 2 times theta, which is the arc secant of x plus 1 divided by 2, plus a constant. And if I simplify this a little bit more, that will give me x squared plus 2x minus 3 divided by 4 times 2 minus 2 times the arc secant x plus 1 divided by 2 plus constant. And then this ends up being x squared plus 2x minus 3 divided by 2 minus 2 times the arcsecant x plus 1 divided by 2 plus a constant. If we want, we could rewrite arcsecant in terms of either arcsine or arccosine, and that will give me an equivalent expression. And also another thing to notice in here is that it depends on the domain of our function. We might need to write down absolute values over here just to make sure that the result is always positive. So that's the answer.